Did you know the universe might not have started with a big bang? What if I told you there's a theory that suggests our universe is one of many, constantly being born and destroyed in an endless cycle? Welcome to a journey through some of the most mind-bending, controversial theories about the universe's origin. We'll dive into 15 astonishing ideas that challenge everything we think we know. From the mysterious concept of a multiverse to the possibility that we live in a hologram, each theory will leave you questioning the very fabric of reality. Stick around to find out which theory suggests our universe could have come from nothing at all, and which one posits that an ancient civilization might have played a hand in its creation. Ready to have your mind blown? Let's get started. The first theory involves the widely accepted Big Bang theory. This theory suggests that the universe began as an extremely hot and dense singularity approximately 13.8 billion years ago. Imagine a point smaller than an atom that contained all the matter and energy in the universe. Suddenly, this singularity started expanding in a colossal explosion, giving birth to time, space, and everything we see around us. This expansion continues today, with galaxies moving away from each other as space stretches. The Big Bang theory is supported by several key pieces of evidence. One is the observation of the cosmic microwave background radiation, the afterglow of the initial explosion, which can still be detected with telescopes. Another is the redshift of distant galaxies, indicating that they are moving away from us, a sign that the universe is expanding. Edwin Hubble's discovery in the 1920s that galaxies are moving away from each other in all directions was a crucial piece of the puzzle. The Big Bang theory has been refined over the decades to include concepts like inflation, a rapid expansion that occurred fractions of a second after the initial explosion, smoothing out the distribution of matter and energy. This theory has shaped our understanding of cosmology and remains the dominant explanation for the universe's origin, but it's not without its challenges. Let's move on to the next theory that offers a different perspective on how everything began. The second theory involves the steady-state theory. This theory proposes that the universe is eternal and unchanging, which stands in direct contrast to the Big Bang theory. According to the steady-state theory, new matter is continuously created as the universe expands. This constant creation maintains a consistent density, making the universe look the same at any point in time and from any location. Imagine a universe that has no beginning or end, where the creation of new galaxies and stars balances out the expansion, keeping everything in a sort of cosmic equilibrium. The steady-state theory was popular in the mid-20th century, but began to lose favor with the discovery of the cosmic microwave background radiation, which the Big Bang theory predicted and the steady-state theory could not explain. Moreover, observational evidence showing that the universe has changed over time, such as the evolution of galaxies and the distribution of quasars, further challenged the idea of an unchanging cosmos. The controversy surrounding the steady-state theory lies in its fundamental assertion that the universe has always existed as we see it today, a concept that defies the evidence we have gathered about the universe's dynamic nature. Despite its decline in popularity, the steady-state theory remains a fascinating alternative, challenging us to consider a universe that is both infinitely old and perpetually new. Now, let's move on to another intriguing theory that adds another layer to our understanding of the cosmos. The third theory involves the concept of eternal inflation. Eternal inflation builds on the Big Bang theory, but takes it a step further by proposing that the universe's rapid expansion didn't stop after the initial explosion. Instead, it continued and is still happening in different regions of the universe. Picture a vast cosmic inflating balloon. While our observable universe formed and settled down into a more stable state, other parts of the balloon kept expanding at an astonishing rate. These regions eventually give rise to their own separate universes, each potentially having different physical properties and laws. This means that our universe could be just one bubble in an endless frothy sea of universes, each with its own unique characteristics. The idea of eternal inflation completely changes our understanding of the cosmos because it suggests that the process of universe creation is never ending. New universes are continuously being born, each one starting with its own Big Bang and developing in ways that could be vastly different from ours. This theory not only expands the scale of reality, but also implies that anything that can happen might happen in some universe somewhere. Think about it, there could be universes where the constants of nature are slightly different, leading to entirely different kinds of stars, planets, and possibly even forms of life. The theory of eternal inflation adds a mind-boggling layer to the multiverse concept and challenges us to think beyond the limits of our own universe. But if you think that's wild, wait until you hear about the next theory, which suggests that our universe might just be a part of a higher dimensional space. The fourth theory involves quantum fluctuation. Quantum fluctuation theory posits that our universe could have originated from the random, momentary changes in energy occurring within a vacuum. Imagine a vacuum not as empty space but as a seething landscape full of fleeting energy shifts. In the realm of quantum mechanics, even a void isn't completely empty. Instead, it's a frothy sea of particles popping in and out of existence. According to this theory, one such fluctuation could have produced a massive amount of energy, sparking the birth of the universe. Think of it like a boiling pot of water where bubbles form and disappear. One bubble grows big enough and doesn't pop, instead giving rise to an entire universe. This concept is revolutionary because it suggests that the universe could have come from nothing at all, defying our intuitive understanding of creation. However, it garners debate for several reasons. First, the idea that something can emerge from nothing challenges fundamental notions of causality and existence. Critics argue that while quantum mechanics allows for temporary fluctuations, the creation of a whole universe is a different magnitude of improbability. Second, while quantum fluctuation theory provides a fascinating explanation for the universe's origin, it still struggles with the question of why such a fluctuation would happen in the first place and what conditions could make it possible. The theory also intersects with the concept of multiple universes, suggesting that if our universe can emerge from a quantum fluctuation, perhaps countless others can too. Each fluctuation could spawn a new universe, leading to an endless array of parallel universes with different properties. Quantum fluctuation theory is intriguing because it offers a completely different perspective on how everything began, relying on principles of quantum mechanics that defy our everyday experiences. As fascinating as it is, the theory also highlights the limits of our current understanding and the need for more research into the fundamental nature of reality. From the subatomic dance of particles to the vast expanse of space, this theory pushes the boundaries of what we consider possible. Now, let's dive deeper into another theory that challenges our perception of the universe, suggesting it might be part of a grander, higher dimensional space. The fifth theory involves the cyclic universe. The cyclic universe theory posits that the universe undergoes endless cycles of creation and destruction. Imagine the universe as a giant cosmic heartbeat, continuously expanding and contracting over vast periods of time. In this model, the end of one universe's life serves as the beginning of the next. Picture an infinite loop where the universe starts with a big bang, expands to a certain point, and then collapses back into a singularity, only to explode again in another big bang. This cyclical pattern proposes that the universe is eternal but ever-changing, with each cycle wiping the slate clean for a fresh beginning. Supporters of the cyclic universe theory argue that it addresses some of the puzzles left unanswered by the Big Bang theory, such as what happened before the Big Bang. Instead of a singular event, the universe is seen as part of an ongoing process. This theory also resonates with ancient philosophical and religious beliefs that depict the cosmos as cyclical. However, it is not without its challenges. One major issue is the second law of thermodynamics, which states that entropy or disorder in a closed system should always increase. Critics argue that if the universe has been cycling for eternity, it should be filled with so much entropy that new cycles couldn't start. Proponents counter this by suggesting mechanisms that could reset the entropy, though these ideas remain speculative. Another point of contention is the lack of direct evidence for the cycles. While some theories and models suggest possible signatures in the cosmic microwave background radiation or patterns in the distribution of galaxies, conclusive proof is still elusive. Despite these challenges, the Cyclic Universe Theory offers a compelling alternative to the traditional Big Bang model. It invites us to think of the universe as not just a one-time event but a continuous, dynamic process, ever in flux and renewal. This concept not only challenges our understanding of time, but also suggests that the universe is far more resilient and intricate than we can currently comprehend. Now, as we continue our journey, let's explore another fascinating idea: the possibility that our universe is just one of many in a vast and mysterious multiverse. The sixth theory involves plasma cosmology. Plasma cosmology challenges the Big Bang theory by focusing on the role of plasma and electromagnetic forces in shaping the universe. While the Big Bang theory centers on gravity and the rapid expansion from a singularity, plasma cosmology suggests that most of the universe's structure is influenced by plasma, the fourth state of matter, along with magnetic and electric fields. Imagine plasma, a highly ionized gas consisting of charged particles, threading through the cosmos like a vast interconnected web. These charged particles interact with electromagnetic forces, creating structures and motions vastly different from what gravity alone would predict. Plasma cosmology proposes that large-scale filamentary structures found in the universe, such as galaxy clusters and superclusters, are better explained by the dynamics of plasma rather than by gravitational forces alone. One of the intriguing aspects of plasma cosmology is its emphasis on laboratory experiments and observations of plasma behavior in space environments. For instance, phenomena like solar flares and auroras demonstrate the powerful influence electromagnetic forces have on plasma. By extrapolating these principles to cosmic scales, proponents argue that plasma's influence could account for many of the universe's features without the need for a singular explosive origin event like the Big Bang. However, plasma cosmology faces significant skepticism. Critics argue that it lacks the predictive power and robust supporting evidence that the Big Bang theory offers, such as the cosmic microwave background radiation and the abundance of light elements like hydrogen and helium. Additionally, while plasma is undoubtedly prevalent throughout the universe, the question remains whether it plays as dominant a role in cosmic evolution as plasma cosmology suggests. Despite these controversies, plasma cosmology pushes the boundaries of our understanding by exploring the potential of electromagnetic forces in cosmic evolution. It invites us to reconsider the intricate dance of forces that shape the cosmos, challenging the gravity-centric view that has dominated mainstream cosmology. As we continue our journey through these controversial theories, let's now turn to another mind-bending idea that suggests the universe might be a massive simulation. The seventh theory involves the holographic principle. The holographic principle proposes that our three-dimensional universe, full of stars, galaxies, and mysterious dark matter, might actually be a projection of two-dimensional information encoded on a distant boundary. This idea is as if everything we perceive in our 3D world, every atom and particle, is akin to a hologram projected from a flat 2D surface. Imagine the universe as a giant movie screen where the true information exists in 2 dimensions, yet we experience it as a fully immersive 3-dimensional reality. This concept stems from black hole physics and the work of physicists like Gerard T. Hooft and Leonard Susskind. who suggested that all the information contained in a volume of space can be represented as a theory on the boundary of that space. One key reason this idea gained traction is due to the mysterious way black holes behave. When something falls into a black hole, information about that object appears to be encoded on the event horizon, the boundary of the black hole, rather than lost entirely. This led to the realization that perhaps all of the universe's information could be similarly encoded on a cosmic horizon. The holographic principle challenges our fundamental understanding of space and reality. It suggests that the fabric of the universe is not as it seems, and that the true nature of our existence might be far stranger than imagined. This theory resonates with the idea that the universe operates on principles far beyond our current ken, hinting that everything we know is just a shadow of a higher dimensional truth. Critics, however, argue that while the holographic principle is mathematically elegant, it remains speculative and lacks direct empirical evidence. Experiments and observations to test this principle are extremely challenging due to the vast scales and conditions involved. Yet, the holographic principle continues to captivate scientists and philosophers alike, pushing the boundaries of how we conceptualize the cosmos. It's a reminder that the universe may hold secrets that are beyond our wildest imaginations, inviting us to ponder the deeper layers of reality. As we journey further, the next theory will take us into the realm of ancient cosmic architects, suggesting that an advanced civilization might have played a role in the creation of our universe. The eighth theory involves the multiverse theory. The multiverse theory suggests that our universe is just one of an infinite number of parallel universes, each governed by its own set of physical laws and constants. Imagine a vast cosmic landscape where every possible outcome of every event actually happens, but in different universes. This means there could be universes where the laws of physics are slightly different, leading to realities that are fundamentally unlike our own. For example, in one universe, gravity might be stronger, stars might form in entirely different ways, or life could evolve based on entirely different elements. The multiverse theory stems from the principles of quantum mechanics and string theory, which imply that there could be countless other dimensions beyond the ones we experience. One compelling aspect of this theory is the idea that every decision we make creates a branching point, spawning new universes where each possible choice is realized. This leads to an unimaginable number of realities, each exploring different possibilities and outcomes. The evidence for the multiverse theory is mostly theoretical, relying on the mathematical frameworks of quantum mechanics and the implications of string theory. Yet, it offers a fascinating explanation for some of the peculiarities we observe in our own universe, such as the fine-tuning of physical constants that allow for the existence of life. Critics argue that the multiverse theory is difficult to test or observe directly, making it more of a philosophical hypothesis than a scientific one. However, supporters believe that as our understanding of quantum mechanics and higher dimensions advances, we might find indirect evidence supporting the existence of other universes. The multiverse theory challenges us to think beyond the boundaries of our own universe, opening up possibilities that stretch the limits of imagination. It suggests that our universe is just a tiny fragment of a much larger, more complex reality, teeming with alternative worlds and dimensions. As we continue, let's delve into another theory that proposes our universe might not only be one of many but also shaped by the presence of other, unseen dimensions. The ninth theory involves string theory. String theory posits that the fundamental building blocks of the universe are not particles but tiny, vibrating strings. Imagine everything in the universe, from the smallest quarks to the largest galaxies, as being composed of these minuscule strings that vibrate at different frequencies. Each vibration corresponds to a different particle, much like how different musical notes are produced by vibrating strings on a guitar. This idea is revolutionary because it attempts to unify all the fundamental forces of nature, including gravity, into a single, cohesive framework. Traditional physics struggles to reconcile the force of gravity with quantum mechanics, but string theory offers a potential solution by suggesting that all forces and particles are manifestations of these underlying strings. One of the most radical aspects of string theory is its requirement for additional dimensions beyond the familiar 3 dimensions of space and 1 of time. To make the mathematics work, string theory proposes up to 10 or even 11 dimensions, most of which are compactified or curled up so small that we cannot perceive them. This challenges our everyday understanding of reality and invites us to consider a universe far more complex than we can directly observe. However, string theory is highly controversial for several reasons. Firstly, it is extraordinarily difficult to test experimentally. The scales at which these strings operate are so tiny that they are beyond the reach of current technology, making direct evidence hard to come by. Critics argue that without empirical evidence, string theory remains more of a mathematical curiosity than a scientific theory. Additionally, the multitude of possible solutions within string theory makes it hard to make specific predictions about our universe, leading some to question its scientific validity. Despite these challenges, string theory has profoundly influenced theoretical physics, offering a new way to think about the fundamental nature of reality. It opens up the possibility that the universe is a far richer and more intricate tapestry than we ever imagined. As we move forward, let's explore another theory that challenges our perception of time itself, proposing that the flow of time might be an illusion. The 10th theory involves white hole theory. White holes are theoretical structures that are thought to be the opposite of black holes. While black holes are regions in space where nothing, not even light, can escape due to their immense gravitational pull, white holes are described as regions where matter and energy are expelled. Imagine a black hole as an insatiable cosmic vacuum cleaner, sucking everything in. In contrast, a white hole would be like a cosmic fountain, spewing matter and energy out. According to this theory, white holes could play a role in the creation of our universe by being the counterpart to black holes in what could be a greater cosmic cycle. Some theoretical physicists propose that when a black hole forms, it could potentially lead to the creation of a white hole. This white hole might then serve as the seed for a new universe, similar to but distinct from the process described in the Big Bang theory. In this model, the collapse of a star into a black hole in one universe could be linked to the emergence of a white hole in another, effectively creating a bridge between 2 separate realities. One of the fascinating implications of white hole theory is its potential to explain what happens to the matter that falls into a black hole. Instead of being lost forever, this matter could be ejected into a different universe through a white hole, contributing to the formation of new cosmic structures. This idea not only challenges our understanding of the universe's origin, but also suggests a potential cyclical nature to cosmic creation, where black holes and white holes work in tandem to perpetuate the existence of universes. However, white hole theory faces significant scientific skepticism. To date, no direct evidence of white holes has been observed, and their existence remains purely theoretical. Additionally, the extreme conditions and energies involved in the formation of white holes make them challenging to study or prove. Critics argue that until we can find empirical evidence or develop a more comprehensive understanding of the mechanisms behind white holes, the theory will remain speculative. Despite these challenges, the concept of white holes offers a captivating glimpse into alternative cosmological models, urging us to think beyond conventional theories and explore new possibilities for the origin and evolution of the universe. As we continue, let's delve into another theory that suggests our universe might be shaped by collisions with other universes in a higher dimensional space. The 11th theory involves the Ekpyrotic model. The Ekpyrotic model suggests that our universe was formed from the collision of 2 higher dimensional branes. Imagine our universe as a 3-dimensional surface floating in a higher dimensional space, much like a sheet of paper in a room. According to this theory, there are other such brains, and the collision of two of these brains could have produced the immense energy required to create our universe. Picture two cosmic sheets colliding and releasing a burst of energy, creating a fiery explosion that gives birth to a new universe. In contrast to the Big Bang theory, which posits a singular origin, the Ekpyrotic model proposes that these collisions happen repeatedly over vast time scales, each collision leading to the creation of a new universe. This process could continue indefinitely, providing a cyclic nature to cosmic history. One of the intriguing aspects of the Ekpyrotic model is its potential to resolve some of the puzzles associated with the Big Bang theory, such as the problem of the initial singularity and the uniformity of the cosmic microwave background radiation. According to this model, the universe started in a nearly empty, cold, and flat state, which was later heated and filled with matter through the brane collision. This contrasts with the infinitely dense and hot singularity proposed by the Big Bang theory. The Ekpyrotic model also draws from string theory, which posits the existence of additional dimensions beyond the familiar four of space and time. These higher dimensions provide the stage for the brains to exist and interact, making the theory a fascinating intersection of ideas from cosmology and theoretical physics. However, the Ekpyrotic model faces its own set of challenges and criticisms. One major hurdle is the lack of direct observational evidence for the existence of higher dimensional brains and their collisions. Additionally, the mathematical complexity involved in modeling such interactions makes it difficult to produce clear, testable predictions. Despite these challenges, the Ekpyrotic model offers a compelling alternative to traditional cosmological theories, pushing us to consider the possibility that our universe's origin might be linked to events in a higher dimensional space. It suggests a grander, more intricate tapestry of reality where our universe is just one chapter in an ongoing cosmic saga. Now, let's move on to the next theory, which delves into the concept of a universe created by intelligent design. The 12th theory involves the variable speed of light. The variable speed of light theory posits that the speed of light was different in the early universe compared to its current value. Imagine light traveling much faster shortly after the Big Bang, a concept that challenges the constancy of the speed of light, which is a cornerstone of modern physics. This idea has profound implications for our understanding of cosmology. One of the key motivations for this theory is to address some of the puzzles in the standard Big Bang model, such as the horizon problem. The horizon problem arises from the observation that the universe appears uniform in temperature and structure, despite regions being so far apart that light couldn't have traveled between them in the available time since the Big Bang. If the speed of light were higher in the early universe, it would have allowed distant regions to come into contact and equilibrate, explaining the observed uniformity without needing to invoke the concept of inflation. Another intriguing aspect of the variable speed of light theory is its potential impact on the fine structure constant, which governs the strength of electromagnetic interactions. A changing speed of light would imply that fundamental constants might not be as constant as we think, opening up new avenues of research into the nature of physical laws. However, this theory is highly controversial and faces significant challenges. One major criticism is the lack of direct evidence and the difficulty in testing the hypothesis. The constancy of the speed of light is deeply embedded in the equations of general relativity and quantum mechanics, making any deviation a profound paradigm shift. Additionally, altering the speed of light could have ripple effects on many physical laws, requiring a major overhaul of our theoretical framework. Despite these challenges, the variable speed of light theory invites us to reconsider foundational principles and explore new dimensions of cosmic history. It pushes the boundaries of our understanding, suggesting that the universe's early moments might have been governed by different physical laws. As we delve deeper into the mysteries of cosmology, this theory serves as a reminder that our quest for knowledge often leads to more questions than answers, urging us to keep an open mind. Now let's move on to another theory that introduces the possibility of a universe created by intelligent design. The 13th theory involves primordial black holes. Primordial black holes theory suggests that tiny black holes could have formed shortly after the Big Bang, playing a crucial role in the early universe. Imagine the universe in its infancy, a hot and dense place where random fluctuations in density caused pockets of matter to collapse under their own gravity, forming black holes. Unlike the massive black holes found at the centers of galaxies, these primordial black holes would be much smaller, perhaps with the mass of an asteroid or even less. These tiny black holes could provide valuable insights into the conditions of the early universe and the fundamental laws of physics. For instance, they could help explain the nature of dark matter, which makes up about 27% of the universe's mass but remains invisible and undetectable through conventional means. If primordial black holes formed in the right quantities, they might account for a significant portion of this elusive dark matter. Additionally, studying primordial black holes could reveal information about the high-energy processes that occurred just after the Big Bang, offering a glimpse into a time when the universe was just a fraction of a second old. The existence of primordial black holes would also challenge our understanding of black hole formation, showing that these enigmatic objects can form in a variety of conditions, not just from the collapse of massive stars. Despite their potential importance, primordial black holes remain a speculative idea, with no direct observational evidence to confirm their existence. Scientists look for indirect signs, such as the gravitational waves produced by black hole mergers or the effects of black holes passing through stars. If detected, primordial black holes could revolutionize our understanding of cosmology, providing a new window into the universe's origin and evolution. This theory illustrates the profound mysteries that still surround the early moments of the universe and highlights the innovative approaches scientists use to explore these cosmic enigmas. Now, let's move on to another captivating theory that suggests the universe might have been designed by an advanced intelligence. The 14th theory involves the anthropic principle. The anthropic principle suggests that the universe's laws and constants appear fine-tuned for life because we exist to observe them. Imagine that the fundamental parameters of the universe, such as the strength of gravity, the electromagnetic force, and the balance between matter and antimatter, are set within an incredibly narrow range. If any of these constants were slightly different, the universe might not support the complex chemistry needed for life to develop. According to the anthropic principle, this fine-tuning is not a coincidence but a necessary condition for our existence. It posits that out of the potentially infinite configurations of physical laws and constants, we find ourselves in a universe that allows for our presence simply because we are here to observe it. This principle comes in two main forms, the weak anthropic principle and the strong anthropic principle. The weak anthropic principle states that the observed values of the universe's physical and cosmological parameters are restricted by the requirement that we are here to observe them. In other words, the universe must have conditions that allow observers to exist at some stage. On the other hand, the strong anthropic principle goes further, suggesting that the universe's parameters must allow for the emergence of observers at some point, implying that the universe is in some way compelled to produce life. Critics of the anthropic principle argue that it is tautological and does not offer a genuine explanation for the fine-tuning of the universe. Some see it as a philosophical rather than a scientific principle because it does not make testable predictions or provide a mechanism for the fine-tuning. However, proponents believe it offers a compelling perspective on why the universe appears as it does. The anthropic principle intersects with other theories, such as the Multiverse theory, which proposes the existence of countless other universes with different physical laws. If many universes exist, each with varied constants, it would not be surprising that at least one of them has the right conditions for life. Our universe would simply be one where the conditions happen to allow for our existence, a natural consequence of a vast multiverse. The Anthropic principle challenges us to think about the relationship between life and the cosmos, suggesting that the universe's very structure might be inherently linked to the possibility of life. It is a thought-provoking idea that invites us to ponder the profound connections between our existence and the fundamental nature of reality. As we approach the final theory in our exploration, prepare to consider the possibility that our universe's intricacies might be the result of a grand design by an advanced intelligence. The 15th theory involves the simulated universe. The simulated universe theory posits that our entire reality, including the Earth, the stars, and even the galaxies, might be nothing more than an incredibly sophisticated computer simulation created by an advanced civilization. Imagine living in a highly immersive video game where every aspect of your environment, including other characters, is generated by a powerful computer. This concept suggests that what we perceive as physical reality is actually a digital construct, designed and controlled by beings far more technologically advanced than ourselves. One of the central arguments for this theory is based on the exponential growth of computing power and advancements in artificial intelligence. As our own technology progresses, it's conceivable that future civilizations could develop simulations so realistic that the simulated beings within them would perceive their world as entirely real. If it's possible for a civilization to create such simulations, then it might be highly probable that many more simulated realities exist than physical ones, making it statistically likely that we are living in one of these digital worlds. Proponents of the simulated universe theory, like philosopher Nick Bostrom, argue that if advanced civilizations can and will create many simulations, the chances of us being in the original, base reality are very slim. This theory challenges our understanding of consciousness and reality, suggesting that our thoughts, experiences, and even our sense of self could be the product of intricate algorithms. However, the theory also raises profound philosophical and ethical questions. If our universe is a simulation, who are the creators and why did they create it? Are they observing us, and do we have any significance beyond the parameters of the simulation? Critics of the simulated universe theory argue that it is unfalsifiable and lacks empirical evidence. They suggest that without a way to test or observe the creators of the simulation, the theory remains speculative. Nonetheless, some researchers propose looking for glitches or inconsistencies in the laws of physics as potential evidence of our simulated nature. The idea of a simulated universe is both fascinating and unsettling, forcing us to question the fundamental nature of existence. It opens up new avenues for philosophical inquiry and challenges us to rethink what it means to be real. Whether or not we are living in a simulation, the theory invites us to explore the boundaries of knowledge and the potential limits of our understanding. This concludes our journey through 15 controversial theories about the universe's origin. Each theory offers a unique perspective, pushing the limits of imagination and challenging us to think beyond the known. Thank you for joining us on this cosmic adventure. Don't forget to like, share, and subscribe for more mind-bending explorations into the mysteries of the universe. The 16th theory involves the concept of a universe from nothing. This idea, proposed by some physicists, suggests that the universe could have emerged from nothing due to quantum fluctuations. Imagine a vacuum not as empty space but as a seething landscape full of fleeting energy shifts. In the realm of quantum mechanics, even a void isn't completely empty. Instead, it's a frothy sea of particles popping in and out of existence. According to this theory, one such fluctuation could have produced a massive amount of energy, sparking the birth of the universe. Think of it like a boiling pot of water where bubbles form and disappear. One bubble grows big enough and doesn't pop, instead giving rise to an entire universe. This concept defies our intuitive understanding of creation because it suggests that the universe could have come from nothing at all. However, it garners debate for several reasons. First, the idea that something can emerge from nothing challenges fundamental notions of causality and existence. Critics argue that while quantum mechanics allows for temporary fluctuations, the creation of a whole universe is a different magnitude of improbability. Second, while the universe from nothing theory provides a fascinating explanation, it still struggles with the question of why such a fluctuation would happen in the first place and what conditions could make it possible. The theory also intersects with the concept of multiple universes, suggesting that if our universe can emerge from a quantum fluctuation, perhaps countless others can too. Each fluctuation could spawn a new universe, leading to an endless array of parallel universes with different properties. Quantum fluctuation theory is intriguing because it offers a completely different perspective on how everything began, relying on principles of quantum mechanics that defy our everyday experiences. As fascinating as it is, the theory also highlights the limits of our current understanding and the need for more research into the fundamental nature of reality. From the subatomic dance of particles to the vast expanse of space, this theory pushes the boundaries of what we consider possible. Now, let's wrap up this journey by reflecting on the incredible diversity of ideas we've explored and what they mean for our understanding of the universe. The 17th theory involves dark flow. Dark flow is a term used to describe a peculiar and unexplained motion of galaxy clusters that seem to be moving in a uniform direction at high speeds, inconsistent with the expected expansion of the universe. Imagine vast clusters of galaxies, each containing billions of stars, all drifting together towards a specific region of the sky as if they are being pulled by an unseen force. This motion is not accounted for by the standard cosmological model, which predicts that galaxy clusters should be moving randomly relative to each other, driven primarily by the expansion of the universe. The phenomenon of dark flow was first detected by analyzing the motion of galaxy clusters using data from the Wilkinson microwave anisotropy probe. Researchers found that these clusters appeared to be moving towards a particular area beyond the observable universe at speeds of up to 1,000 kilometers per second. The key mystery here is what could be causing this coherent motion. Some scientists speculate that dark flow could be the result of gravitational influences from massive structures outside our observable universe. In other words, there might be cosmic structures or even other universes exerting a gravitational pull on our universe, affecting the motion of galaxy clusters in a way that we cannot directly observe. This idea challenges the notion that the observable universe is all there is, and suggests that our universe might be part of a much larger and more complex reality. However, dark flow remains highly controversial. Critics argue that the data could be interpreted in different ways and that more observations are needed to confirm the phenomenon definitively. Additionally, the concept of influences from beyond the observable universe is speculative and difficult to test with current technology. Some researchers propose alternative explanations, such as local anomalies in the cosmic microwave background radiation or statistical noise in the data. Despite these challenges, the study of dark flow continues to intrigue cosmologists and physicists, prompting them to consider new ways to explore the universe's limits. It serves as a reminder that our understanding of the cosmos is still evolving, and that there may be forces at play that we have yet to discover. As we reflect on this, dark flow pushes the boundaries of our knowledge and invites us to explore the possibility of a universe that is far more interconnected and mysterious than we can currently comprehend. Whether dark flow is ultimately proven to be a genuine phenomenon or not, it highlights the dynamic and ever-changing nature of cosmological research, urging scientists to look beyond the known and question the very fabric of reality. The 18th theory involves superfluid vacuum theory. This theory proposes that the vacuum of space behaves much like a superfluid, a state of matter with zero viscosity that can flow without any loss of kinetic energy. Imagine the vast emptiness of space not as a simple void but as a complex dynamic medium that can flow and move effortlessly. In the realm of superfluids, particles move in a coordinated way, allowing them to pass through obstacles without resistance. This idea suggests that the vacuum could have properties similar to this, profoundly affecting the behavior and structure of the universe. According to superfluid vacuum theory, the vacuum is not empty but filled with a substance that behaves like a superfluid, affecting the movement of particles and the propagation of forces, including gravity. This perspective challenges traditional views by proposing that space itself has intrinsic properties that influence the fundamental forces of nature. One of the key implications of this theory is its potential to unify quantum mechanics and general relativity, two pillars of modern physics that currently stand in conflict. By treating the vacuum as a superfluid, the theory offers a novel way to reconcile these two frameworks, potentially leading to a more cohesive understanding of the universe. The theory also draws from the behavior of known superfluids like liquid helium, which exhibits extraordinary properties at temperatures near absolute zero. For instance, superfluid helium can climb walls, flow without friction, and create vortices that remain stable indefinitely. By analogy, superfluid vacuum theory suggests that the vacuum of space could similarly exhibit unique behaviors that shape the cosmos. Critics argue that while the theory is mathematically intriguing, it lacks direct observational evidence. The properties of a superfluid vacuum are challenging to test and observe with current technology, making it difficult to validate the theory experimentally. Additionally, the complexity of modeling such a vacuum and its interactions with matter and energy presents significant theoretical challenges. Despite these hurdles, superfluid vacuum theory pushes the boundaries of our understanding, inviting us to consider space not as an empty stage but as an active, dynamic participant in the cosmos. It suggests that the very fabric of reality might be far more complex and interconnected than we currently comprehend. As we continue to explore these revolutionary ideas, this theory serves as a reminder of the vast potential for discovery that still lies ahead. Now, let's move on to reflect on the incredible diversity of ideas we've explored and what they mean for our understanding of the universe. The 19th theory involves the concept of a mirror universe. The mirror universe theory suggests that there could be a parallel universe where time runs in the opposite direction to ours. Imagine a universe that is a mirror image of our own with the arrow of time reversed. In this alternate cosmos, events would unfold backward from our perspective. This means that what we see as the future would be the past in the mirror universe and vice versa. Think of it as watching a movie in reverse. While everything still happens, the sequence of events is inverted. The mirror universe theory challenges our conventional understanding of time and causality. In our universe, the second law of thermodynamics dictates that entropy, or disorder, always increases over time, giving time its directional flow from past to future. However, in a mirror universe, entropy would decrease over time, leading to a state of order rather than disorder. This fascinating idea stems from considerations in theoretical physics and cosmology that explore the fundamental symmetries of the universe. Some physicists propose that the Big Bang could have produced not just our universe but also a mirror counterpart. This twin universe would have the same physical laws but with reversed temporal direction. One intriguing implication of the mirror universe theory is its potential to solve some of the puzzles in modern physics. For example, it could offer insights into the nature of dark matter and dark energy, which remain enigmatic. If our universe and the mirror universe interact in subtle ways, it might explain some of the strange phenomena we observe in the cosmos. Critics of this theory argue that it is highly speculative and lacks direct empirical evidence. The concept of a mirror universe presents profound challenges for observation and experimentation, making it difficult to test. Moreover, the notion of time running backward contradicts our everyday experiences and intuitions, raising questions about the practicality of such a theory. Despite these challenges, the mirror universe theory invites us to expand our understanding of time and reality. It encourages us to think beyond our conventional perceptions and consider the possibility of a cosmos far more complex and interconnected than we can currently imagine. By exploring the concept of a mirror universe, we push the boundaries of cosmological thought, opening up new avenues of inquiry and discovery. As we continue to delve into these revolutionary ideas, the mirror universe theory serves as a reminder that our journey to understand the universe is full of unexpected twists and turns. Now, let's move on to reflect on the incredible diversity of ideas we've explored and what they mean for our understanding of the universe. The 20th theory involves the concept of an antimatter universe. The antimatter universe theory posits that there could be a counterpart to our universe composed entirely of antimatter, formed during the Big Bang. Imagine a universe where every particle of matter is replaced by a corresponding antiparticle. In this mirror universe, protons are substituted by antiprotons, electrons by positrons, and so on. This fascinating idea stems from the principles of particle physics, where for every type of particle, there exists an antiparticle with the same mass but opposite charge. When matter and antimatter come into contact, they annihilate each other in a burst of energy, a property that raises profound questions about the nature of the cosmos. According to this theory, during the Big Bang, equal amounts of matter and antimatter were produced. However, in our observable universe, we see a predominance of matter, leading scientists to speculate about the fate of the antimatter. One possibility is that an entire universe made of antimatter exists parallel to our own, separated in such a way that the two realms do not interact, preventing mutual annihilation. This antimatter universe would look similar to ours, with stars, galaxies, and possibly even life, but composed of antiparticles. One of the intriguing implications of this theory is its potential to explain the mystery of the matter-antimatter asymmetry in our universe. If an antimatter counterpart exists, it could balance the scales, adhering to the laws of physics that dictate the creation of equal quantities of matter and antimatter. However, there are significant challenges to this theory. The lack of observed annihilation events, which would produce detectable gamma rays, suggests that large regions of antimatter are not present within our observable universe. Additionally, the means by which matter and antimatter could have become segregated into distinct universes remains speculative. Despite these hurdles, the concept of an antimatter universe captivates the imagination, urging scientists to explore new frontiers in both theoretical and experimental physics. Efforts to detect traces of antimatter continue, using advanced instruments on Earth and in space. As technology and our understanding of particle physics evolve, we may uncover evidence that sheds light on this enigmatic theory. The antimatter universe theory challenges our perception of reality, suggesting that the cosmos may be more symmetrical and balanced than it appears. It opens up possibilities for a richer, dualistic framework of the universe, where matter and antimatter coexist in separate but equal realms. As we reflect on this diverse array of theories, we are reminded of the vast, uncharted territories of knowledge still awaiting discovery, each theory contributing to our collective quest to understand the origin and nature of the universe. The 21st theory involves variable physical constants. Variable physical constants theory posits that the fundamental constants of nature, such as the speed of light, the gravitational constant, and the fine structure constant, might not be fixed but could change over time. Imagine a universe where the very laws that govern it are not immutable. Instead, they evolve, causing profound effects on the cosmos's structure and behavior. For instance, if the speed of light were faster in the early universe, it would allow regions separated by vast distances to communicate and equilibrate, potentially solving the horizon problem without invoking the concept of inflation. Similarly, if the gravitational constant varied, it would influence the rate at which structures like stars and galaxies form and evolve. One of the key motivations for this theory is to address some of the lingering puzzles in cosmology that the standard model struggles to explain. For example, the fine structure constant, which dictates the strength of electromagnetic interactions, appears fine-tuned to allow the existence of complex chemistry and life. If this constant were to change even slightly, it could result in a universe where atoms and molecules form differently, possibly altering the entire fabric of reality. Proponents of variable physical constants theory suggest that these changes could be gradual and linked to the universe's expansion and evolution. By observing distant astronomical objects and comparing them to nearby ones, scientists look for subtle variations in these constants over time. Early results hint at possible changes, though the evidence is not yet conclusive. Critics argue that this theory challenges the foundational principles of physics. Most physical laws assume that these constants are indeed constant, providing a stable framework for scientific inquiry. Any variation would require a major re-evaluation of existing models and could introduce complexities that are difficult to reconcile with observed phenomena. Additionally, the current lack of definitive empirical evidence makes it challenging to test this theory rigorously. Despite the controversies, exploring the possibility of variable physical constants pushes the boundaries of our understanding and invites us to consider a more dynamic universe. It forces us to think beyond the fixed parameters that have long defined our scientific worldview, opening up new avenues for research and discovery. As we delve deeper into this intriguing idea, we are reminded of the ever-evolving nature of science and the continuous quest to uncover the secrets of the cosmos. Now, as our journey through these revolutionary theories nears its end, let's reflect on the incredible diversity of ideas we've explored and what they mean for our understanding of the universe. Thank you for joining us on this cosmic adventure, and don't forget to like, share, and subscribe for more mind-bending explorations into the mysteries of the universe. The 22nd theory involves gravitational waves from the Big Bang. Gravitational waves are ripples in the fabric of space-time caused by some of the most violent and energetic processes in the universe. Imagine throwing a stone into a pond and watching the ripples spread out from the point of impact. Similarly, gravitational waves travel outwards from their source, carrying information about the events that created them. When it comes to the birth of the universe, these waves could hold key insights. According to the theory of general relativity proposed by Albert Einstein, gravitational waves are produced when massive objects accelerate, such as during the collision of black holes or neutron stars. But scientists believe that the most powerful gravitational waves were generated during the very moment of the Big Bang itself. Detecting these primordial gravitational waves could provide a direct glimpse into the universe's earliest moments, far beyond what we can see with light. These waves would carry information about the state of the universe fractions of a second after its inception, offering clues about the conditions and mechanisms that triggered the Big Bang. The detection of gravitational waves is a relatively recent achievement, thanks to advanced observatories like LIGO and Virgo. These facilities use incredibly sensitive instruments called interferometers to detect the tiny distortions in space-time caused by passing gravitational waves. In 2015, LIGO made the groundbreaking discovery of gravitational waves from a pair of merging black holes, proving that these elusive ripples can indeed be observed. Since then, researchers have been working to refine their techniques and search for the faint signals of primordial gravitational waves. If found, these waves could help solve some of the biggest mysteries in cosmology, such as the nature of inflation, a rapid expansion that occurred in the universe's first moments. Primordial gravitational waves could provide evidence for this inflationary period, confirming theories about how the universe grew from a subatomic size to a vast cosmic expanse in a fraction of a second. Additionally, discovering gravitational waves from the Big Bang could offer insights into the fundamental forces that shaped the universe, including gravity itself. They could reveal new information about the behavior of space-time under extreme conditions, potentially leading to breakthroughs in our understanding of quantum gravity and the unification of the fundamental forces. However, detecting these primordial waves is an enormous challenge. The signals are expected to be incredibly faint, buried under cosmic noise and requiring unprecedented sensitivity to observe. Future missions, such as the space-based observatory LISA, aim to overcome these challenges by detecting lower-frequency gravitational waves with greater precision. Despite the difficulties, the pursuit of gravitational waves from the Big Bang represents one of the most exciting frontiers in modern physics. It offers the promise of unlocking the secrets of the universe's birth and gaining a deeper understanding of the cosmic origins. As we continue to refine our instruments and techniques, we move closer to unraveling the mysteries of the very first moments of existence. This exploration not only pushes the boundaries of science, but also deepens our connection to the cosmos, reminding us of the profound and intricate tapestry that is our universe. In summary, we've journeyed through some of the most fascinating and controversial theories about the origin of the universe. From the widely accepted Big Bang theory to the mind-bending concept of the simulated universe, each theory offers a unique perspective that challenges our understanding of reality. We've explored the possibility of an eternal, unchanging universe with the steady-state theory, and delved into the idea of our universe being one of many in the vast multiverse theory. The holographic principle and the theory of a mirror universe have pushed us to rethink the very fabric of our existence, suggesting that our reality might be a projection or even a reverse counterpart to another cosmos. The variable speed of light and the concept of primordial black holes have introduced new ways to look at the forces and phenomena that shape our universe, while the anthropic principle has led us to consider the fine-tuning of our universe for life. The revolutionary ideas of superfluid vacuum theory and gravitational waves from the Big Bang have expanded our understanding of space itself. As we reflect on these theories, we invite you to ponder which one you find most compelling. Is it the idea that our universe is part of an endless cycle of creation and destruction, or the notion that we might be living in an advanced simulation? Could it be the thought-provoking concept of a universe emerging from nothing or the possibility of unseen forces shaping the cosmos? Share your thoughts in the comments below and join the conversation on the mysteries of the universe. Don't forget to like, share, and subscribe for more mind-bending explorations into the wonders of space and beyond. Thank you for joining us on this cosmic adventure.